So I do just want to go over just one of the last few points on triplet, this and that. And then again, so I kind of like, I just am too long-winded. As I get older, I become more long-winded. Well, hell, right? Every video I summarize what we did before. So let me summarize that energy, the Coulomb part of the Hamiltonian has a weirdness to it because there's part of it that makes sense, which are just electrons interacting with each other. But then you get this cross term. It's like a FOIL term when you're doing A times A plus B squared, right? You got A squared plus B squared, and that makes sense. That's the Coulomb integral, which are just two electrons interacting with each other. But then you get the cross term, and that's the J part. And again, that comes from the antisymmetry of the wave functions. I rewrote this out from last time. I realized I can still rearrange these, and you can see that it gets funky because I don't have the absolute value of the wave function anymore. I've got, on the Coulomb integral, I've got psi1 star R1, psi1 R1, but in this cross term I got psi1 R2, and then the same for the other guy, just permuted, right? So you can't say that this is the absolute value of the location of the first electron because this is describing electron 1 and electron 2 simultaneously. That's why we call it an exchange term. It's just bizarre, and I can't give you any explanation for what the heck it means or what it, I mean, I know what it's doing. It's changing the energy of the atom, of the multi-electron atom. I get that. It's what makes triplets lower than singlets. Usually, overwhelmingly that's true, although sometimes not. It's just the way that these exchange labels, I just don't know. I can't describe that, what that means. Okay, here is my best attempt to graph this change in energy for singlet versus triplet. And apparently, despite the fact that we have supercomputers, this is still considered somewhat controversial. And this picture I'm about to present apparently is considered perhaps somewhat dubious. And I don't get that, but anyway, like I say, we're on the edge of grad school, and there's a good reason for that. Okay, singlets. Remember that singlets have symmetric space wave functions. So I've drawn this in a very symmetric way. And when I square them, which is the only thing that has meaning, you see the wave function actually tends to like augment itself in the in-between spaces. Now that means that these electrons, if you want to think an electron is on this side and electrons on that side, it means that they're getting awfully close together, right? So their wave functions are blending together. That's bad, by the way. That means the electrons are bumping up next to each other. They don't like that. That's an energy raising. Now, a triplet has anti-symmetric space wave function. So I've drawn that with odd symmetry, right? So I drew one with even symmetry, and here's odd symmetry. Now it has a node. As a result, when I draw the wave function squared, the electrons are now staying far away from each other, which is good, right? So maybe that's why triplets have lower energy. I can tell you I've seen other explanations, and that's something. Okay, now here's a neat thing. And here's what I want to test somewhere. One of the most consequential things to this, other than I mentioned that triplets are lower in energy, so organics absorb light. They unfortunately tend to fall in a excited triplet state. Then they're primed to react with oxygen. Oxygen's a triplet, it's a triplet. It's like radical chemistry, which is explosive. And that's why things oxidize. That's pretty important. Here's another one. Magnets. Breaking Bad, right? You guys, oh, I forgot, Disney fans. Anyway, radically, I'd like to see Disney make Breaking Bad. Actually, that could be like major dark, because, sometimes like the bright, shiny people are the ones you gotta look out for. Okay, so notice that, what would you call this? Triplet or singlet?
Singlet. Right,
so I'm drawing like let's say I'm drawing like an iron compound. I would call that singlet. Would you think that'd be magnetic?
No.
Right. So remember, electrons are magnetic. That's how you direct electrons in old cathode ray TV tubes. Yeah, maybe you had like the old TVs when you were young, the old screen, vacuum tube TVs, and those work by raster scanning electron beams with magnets. So if I make an organometallic compound, let's say it has two irons. This is not magnetic, and the reason it would not be magnetic is they're not close together. This would be like a bridging. This organometallic would have some kind of bridge some kind of ligand that's big. So the two metals are far away from each other. Now, when they're far away from each other, this weird cross-term deal gets small. The J integral gets small. So hopefully, so as much as I can't really explain this, I can kind of do so with an example question.
I thought magnetism mostly had to do with if the spin's aligned.
Yeah, this is not aligned.
Oh, okay.
Right, that's not aligned.
Okay,
So,
well, I
so
thought
right.
you were doing a different explanation.
No. Those spins are not aligned, right? So
Okay.
up down counts as unaligned. This is aligned.
Okay.
Right. Now, what's happening here is the J integral is non-existent because those two atoms are the electrons that give it possible magnetism. They're too far away, and that makes this part like it suppresses that. So as much as I can't give you a nice little folksy explanation for what's happening here with this, with the second orbital having two different electrons. I can't give you a folksy explanation, but I can tell you that if these unpaired electrons are far away from each other, they're going to be anti-ferromagnetic. They're going to be up and down, which again, that's kind of normal behavior for magnets, right? But now, if they're close together, let's say that there's an oxo bridge, like iron oxide, when they're close together, then this thing can get big. And it favors the high spin state, the triplet state. If so, then these things suddenly want to do what magnets normally don't want to do. Remember, this is not normal magnetic behavior. This is, for like bar magnets, right? The two are lined up. And that's because they're close together. And of course, if I'm talking about like iron oxide, the material, rust is not very magnetic, but it is not magnetic. The word diamagnetic, it is not diamagnetic, it is magnetic. So you can imagine that these electrons, each one which is fairly electrons are really quite magnetic. And you get a whole bunch of them, then you got yourself a pretty good magnet going on here. So anyway, just wanted to show you that. That's the consequences of these exchange integrals. And I don't know, I kind of like magnetism. I think it's kind of neat. I like playing with magnets, that's why. And this explains why that happens. We also know why the Earth is turning to dust as well. I just explained that. That's kind of cool. And I don't need deities to explain that. So, any questions before we move on to something wildly different? Tell you what, let me tell you one other neat thing. You notice how I was solving the energies this way? By integrating wave function on the left, wave function on the right, operators in between. Because those wave functions are artificial. Remember, I can't solve the real wave functions when I include a Coulomb integral. I'm just making this jazz up completely. Well, where do I make this stuff up from? Now, it's sensible to say, if I'm describing H minus, I'm going to use hydrogen wave functions. And if I'm describing helium, what you do, I haven't emphasized this, but what you would do is solve the hydrogen atom for a +2 nucleus. It's incredibly easy, right? You just change the Coulomb operators. There's nothing to it. The problem is that that's not right. We don't know what right is. We can't figure it out. That's a good first attempt. But I have every reason to believe, when I'm describing multi-electrons, that is not correct. So let me tell you the way that we try to do this. Let's say, we're describing helium in this state. Let's make it a singlet, 1s, 2s. Let's make it helium in the excited state. It's a singlet, but I've got 1s and a 2s. Now I'm trying to come up with a wave function. So what I do is I give the 1s electron like this, and I make the 2s, the 2s has a node like this. Now again, I've maybe compressed them. I've made some adjustments. I've taken hydrogen, I made an adjustment for a more positive nucleus. And I just say, okay, well, the 1s is like this and the 2s is like that. Notice that the 2s has a node. And I'm just going to use that. again, knowing that this is ultimately incorrect. So what we do, what people on computers used to do quite a bit in the 80s and 90s, and still a couple people do, they take these functions and they start making adjustments. I don't know, they won't change them radically, right? They'll do things. They'll try to make some adjustments, right? It's sensible things. Maybe they do this. Or even, well, not that. I think we're not going to do anything too crazy. We're not going to add nodes or something like that. Anyway, so what they do is they take those functions and adjust them in, some kind of, logical search pattern-ish way, and then they check what the energy is. And if they find that one of these is a lower energy, then that's better. And yeah, so there you go. That's what modern theory of electronic structure, that's what that's all about, is trying to come up with atomic orbitals for multi-electron. Again, for a single electron, I got that. That is done for hydrogen. But as soon as I'm describing H- or helium or freaking anything, the hydrogen wave functions are a good start, but they're not right. So we start doing little computer searches to change those like atomic-like functions to give lower energies, and they spend months trying to tweak these, and when they find the best tweak possible, the theoreticians publish a result, and then other computational chemists use them. So anyway, so that's one of the things, that's one of the consequences of what it means for us to not know what the wave functions are, and to use this very artificial construct in quantum mechanics. Again, we don't know what the real wave functions are for anything past hydrogen. It's funky. Okay, anyway, with that said, you also know about shielding. Shielding and orbital energies. Now, you had this in high school, but you're going to put a bit more of a face on this, and you're also doing part of this on your homework. Okay, now, I've been doing this. I've been writing this ad nauseum. 2s to 2p. Here's the 1s. I'll just write out 1s just so you don't get lost. Okay, so 1s doesn't change, but when you add multi-electrons, you know that, all right, you were at one point, especially in freshman, writing out atomic configurations for various elements in the periodic table, right? You can remember 1s2, you remember doing this? Okay, what should I be writing next? Because it's not, so the 2s and the 2p are not the same for multi-electrons. What's next? What's lower in energy? No, 2s is next. And then 2p. Don't you remember doing that? So if you were writing, what's hydrogen, helium, what's after hydrogen, helium? Lithium. Yeah, Li, 1s2, 2s1. Why didn't you write 2p1? I mean, S and P are identical. They're degenerate in the hydrogen atom, but you know that you actually wrote 2s. 2s. What's after lithium? Boron? Boron's full, right? Magnesium?
I always think aluminum.
Yeah, why don't we? Yeah, I know. I should know this. I'm pretty sure boron is next. Boron is?
It's beryllium.
Oh, beryllium.
Beryllium's next.
Then boron. Wait, seriously, boron?
Then boron.
Beryllium, then boron.
Then boron.
Okay, and so boron, right, boron's in the P block. That's why I get it. Right, so you have an order. You did this. I wasn't teaching your freshman class. I don't know what you learned, but you should have been doing this, right? So I know that you've seen this before because it's one of the things that we know freshmen can handle, to learn basic atomic structure. Okay, so hydrogen formally has S and P degenerate, but when you do multi-electron atoms, which again is everything, then the S's are actually lower than P's. And again, that's because I don't have, I mean, we happen to know this experimentally, but you don't have a good way to do it theoretically. Now, what comes next? The orbital?
3s, right? Oh, 2D. No,
3s.
3s. 3s. Okay, next?
3p. 3.
No, 2, 3.
3p.
4s and 3.
And what?
4s.
Hold on, what about the D?
3.
No, 4s, you were right the first time. Don't doubt yourself. 4s comes next, then 3d. And yada, 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 yada. Now, how the heck did that happen? Why was, why is 2s lower than 2p, again, formally degenerate? 3s, 3p, 3d, formally degenerate in the hydrogen atom, no longer degenerate, and the freaking 4s gets down in between the 3 space. That's weird. Remember that those things have nodes, right? So definitely 4s is higher in energy than 3s because 4s has an extra node, and that's very devastating for kinetic energy. It increases kinetic energy. Now, the 3p has one less radial node, but then it has angular nodes, so that increases its energy. Okay, the reason that happens is on your homework. It is due to, where am I at? It is due to shielding. It's due to shielding. And the way that works is, okay, so here we go. I'll just do the 2s, and you're doing this on your homework. Here's the wave function here, R. Here is the 2s. Again, it has a node. And here is a 2s and a 2p. Again, a 2p would have no nodes because it's the first of its kind, right? So the first of its kind doesn't have a node. Now, it turns out that the average R for a 2s is 6 Bohrs, and the average R of a 2p is actually 5 Bohrs. So that struck me as odd. I was actually doing this calculation last year for a homework set, and I looked at that and I thought, well, that's weird, because I know the reason that shielding exists is that the 2s is closer. What's wrong with my writing today? It's closer to the nucleus than a 2p, which is further away. Okay, so the 2s is closer to the nucleus, and electrons like protons, so that's an energy lowering thing. The 2p is further away, and so that raises its energy. So therefore, 2s than 2p. And then that also explains the other trends. So that's shielding. So not only is the s electron closer, it also screens away the proton for the 2p, so the 2p gets less juice. So the s steals the positive juice and takes it from the p, and so the s drops in energy and the p is raised. Now, what's odd is, I knew this, and this is something you probably should have had as freshmen as well, and I wanted you to prove that, and I did this calculation, and I found the exact opposite. This says, on average, that the p state is closer than the s. And I look at this, and I'm like, well, that actually kind of looks right. This p looks, because of not having a node, that's why, because it doesn't have a node, it looks a little bit closer on average than the s. I actually drew this fairly well. But then I realized, but what I then did was this. And you're doing this on your homework, by the way, so I'm just telling you what's going to happen. I actually did the close distance. I looked at the absolute value of the wave function times r, integrated over close distance. And then I did the same thing for the 2p. And don't forget r squared. Don't forget the r squared, right? Now, when you do this, and you're doing this on your homework, and by the way, of course it's a definite integral, it's a pain. do it on Wolfram Online, and I put a link, excuse me, I put a link in the homework. And then what you find is that actually, by nearly a factor of 10, more electron density of the 2s is closer to the nucleus than the 2p. Now, if you go all the way, if you make that infinity, then you get the result I just wrote here. But when you're looking at close distances, 0 to not far away, the s electron, and you can see that in the graph here too, so it's kind of funny. I can see that this is clearly correct. Most of the s electron is way closer to the nucleus than the p. That institutes shielding, that makes its energy lower. But when you look at the whole thing, then the opposite is true. So anyway, on your homework, I have you do that. And what this is proof that the 2s is actually closer to the nucleus than the 2p, and that's why you get this odd ordering. So the next thing I wanted to also cover about multi-electron this and that is this is a subtlety. So this is called spin. So the next thing, this is actually the subject of my PhD thesis. Spin-orbit coupling. So notice that when I wrote out the Hamiltonian on the first, oh no, not the first day, like third week of class, we started with the Schrodinger equation. And I said something remarkable. I said that energy is kinetic plus potential. And you were like, sure. Well, where did I get that? I don't know. I don't know who discovered kinetic energy is kinetic energy. I mean, somebody at some point came up with that, because I don't think cave people had it. Potential energy is potential energy. Someone came up with these concepts, and we accept them, and just use them without thinking, and I'm pretty sure it's okay. I think it's been tested enough. And I created a Hamiltonian with that. Well, what if there's other things in there? Apparently there's this dark energy stuff, right, that wasn't in the Hamiltonian for galaxies. And when they added it, all of a sudden everything made more sense. Just don't know what it is yet. So my point being is that I wrote things into the Hamiltonian, kinetic energy and potential energy, that made a lot of sense to you, but did I write everything that I could possibly write? The answer is no. So there's this thing called spin-orbit coupling. And again, I actually studied this as my PhD thesis. I looked at compounds with very low spin-orbit coupling, but they behave as though they don't. And I'll explain that was just a mouthful. What does that mean? Okay, so what happens is, take an electron, and let's make it spin around and around and around. What do spinning electrons do? What do they create? Magnetic fields, right? You know that. Right? In a little circle. So it's like a little toroid. Sorry, I was about to say toroid. That's way too advanced. A donut. It creates a donut. It's a donut of magnetism, right? Little B field. Now recall that that's how toys work. Those little slot car racings. I remember when I was 6 or 7, I wanted one of those so freaking bad. It looked like so much fun. And I got one, and about 30 seconds later, I'm like, this is freaking boring. All right. So electricity going through a coil of wires creates a magnetic field that puts a torque on a wheel that causes it to turn, right? That's how that works. Okay, now, what kind of electron is spinning in an atom? 1s, a 1p, a 1d, 2s. I'm fooling with you. You are. Huh? Give me something. Someone say something. Back people, you never talk. Give me an electron that's turning.
All of them.
You don't know. 1s's are not turning. They have no angular momentum. S states have no angular momentum. I'm talking about rotating.
So 2p.
2p. And what about a 1p? Right, doesn't exist. Right, doesn't exist. Right. So a 2p, 3p, 3d. These guys are rotating. The electrons are rotating. Now, again, I can't really visualize that. You know, it's one of the things that always frustrated me. An S state is round, but it's not rotating. What? This is a dumbbell, and that's rotating. Yeah, I don't get it. I have no idea. I mean, it has a node. That's the point. It has a node. That makes it rotating. I never understood that, and I probably never will. Okay, so if the guys with L equals 1, 2, 3, 4, blah, 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 are rotating, they have a magnetic field. Guess what else has another there's another magnetic field in the room. Where is it from?
Earth.
The Earth. Yes, but it's weak. There's another one that's very close.
The nucleus.
The moon. You said it wrong. You should have said the moon. No, the certain nuclei. Protons are magnetic. Now, their magnetism is shockingly weak. Right? And now, you all did, a bunch of engineers I know, did you have organic?
Yes.
Right, you had to take that. You had organic lab. You learned about NMR. Well,
Yes.
you cut yourself, you didn't,
Yeah.
you wanted to kill yourself before that's what, anyway. So you learned about NMR, right? And proton NMR, right? So not every nucleus is magnetic. You can't do NMR on certain things. Like you can't do NMR on carbon-12. You can do NMR on carbon-13. That's an isotope. But anyway, but protons, neutrons are magnetic. Now, if you have an even, maybe you learned this. If you have an even number of protons and neutrons, then it's not NMR active, it's not magnetic because all the magnetism cancel out. They're like little bar magnets. If you got one spin up and one spin down, they'll pair and they'll cancel their magnetism out. There's no helium NMR. Helium is a proton and a neutron. There's no helium NMR because one spin up and one spin down and it cancels. The nucleus is not magnetic. There's no helium NMR. But there is a hydrogen NMR. Lots of things have magnetic nuclei. So that means this guy has its own B field, and guess what? They interact. So here's the thing. Remember, I was telling you that a Hamiltonian is something that I created that describes energy, and I started you out with something that you're so used to, you just accepted it. Oh, of course there's kinetic energy. Oh, and then I'm like, oh, well, there's a bond, and it's like 1/2 kx squared. Oh, of course that's what a bond is. It's like a spring. Coulomb's law for hydrogen. Oh, of course Coulomb's law, that's energy, and I know that's 1/r. All right, well, there's energy in magnetism too. I just didn't write it down, but now I'm going to. And guess what? It's going to completely mess with things. Okay, so the way that works, so this is called spin-orbit coupling. Therefore, there's an interaction. And the Hamiltonian, so what you have to do is you have to add this to the Hamiltonian. And the way it looks is, tell you what, let me write out the whole thing. Let me write out the whole thing. I really can't. I can't do that enough. I'm just going to get rid of the constants because I'm kind of out of time. Okay, so I've got kinetic energy for the first electron, kinetic energy for the second electron. I've got Coulomb for the proton, first electron, second electron. I'm just getting rid of all the constants. The interaction of the two electrons. And then I've got the spin orbit part. So here's the thing that that I'm talking about that I've never described before. It's a really weird phenomenon. Okay, speed of light, by the way, 1/r. Now, and I'll also tell you where this comes from because this is going to look like it's from outer space. Now, this is the potential. This is the potential energy of the electron inside of the atom, which is unfortunately a very complex thing. L dot S. So this is the spin orbit Hamiltonian. Now the way this works is, it's kind of obvious. What you do is S, so if you have S, if you, I don't think I've described this before, it's on your homework. So basically you've got a bunch of constants, which is the derivative of potential with respect to R, mass c squared, a bunch of constants, 1/r, yada, yada, yada. But the way this works is the spin on a, let's do an eigenvalue equation. Right, and spin operator on beta minus h bar over 2. Okay, so that's easy. If you ask what's the angular momentum of a 2p state, sorry, let me write it more professionally. Of course you get 1 times 1 plus 1 h bar, right? L times L. Oh, that's L squared, isn't it? That's L squared. Oh, yeah, this is what you get. Right? Let me, in case you got a little bit flummoxed by that, let me do a 3D. So a 3D is 2 times 2 plus 1, L times L plus 1. Okay. So that's how those operators work. That's how the operators work. Not much to it. And what it does is it changes the energy of P and D states. So let me look at what that's like. So if I've got a hydrogen, and this is also true of the hydrogen atom. So I've got a 1s state. Now 1s state is not affected, right? Because it's not rotating. The electron doesn't rotate. It doesn't build a magnetic field that interacts with the magnetic field of the proton. So its level does not change. But now you got three 2p states. You got 3 of them. So what happens is they're going to split as so, based on their spin orbit coupling. And I forgot, like, I think this might be like Z, and that's X and that's Y, something like that. I don't quite remember. And what would happen is that normally when you look at hydrogen atoms, and what you do is you energize them and look at the fluorescence, and you would see 1 peak for a 2p to a 1s transition. What you actually see are 2 that are very, very close together. Now, one thing I want to emphasize as we get to the next section is that this splitting is a few wave numbers, right? Now, you know this splitting is on the order of, right, it's 91 nanometers over n squared over 4 minus 91 nanometers over 1 squared, right? So that's that energy difference, right? So this is 2p. You know what I'm doing, right? This is a, minus, right? So when I'm drawing this energy difference, recall that the energy of a hydrogen atom is minus 91 nanometers over n squared. Right, so I put the 2p minus the 1s state. That's how I did that, by the way. Remember, this is also minus 13.6 eV. I'm putting this in spectroscopic terms because we're doing spectroscopy on Monday. Now, big number or little number in terms of energy. Now, remember, you want to multiply that by the speed of light. That gives you 1 over the speed of light. That gives you energy. But what do you think? Is this a big energy difference or small? What do you think? Okay, visible light, 400 nanometer is blue light. Red light is 700 nanometers.
Shorter wavelength, higher energy.
Big. This is a gigantic energy. This is in the UV. This, in your eye, blinds you. All right? This is huge energy. All right? So remember, 400 nanometers blue light. Below that is UV. This is in the X-ray region, right? Pretty much. Okay, wave numbers. Now they're both energy scales, but I'm doing this intentionally because you have to get used to this for the next section. Small or big? Here's a hint. Look at it.
Small.
Small, incredibly small. This is lower in energy than you look at in an FTIR. It's less energy than an FTIR spectrometer. So tiny, tiny. So for H atoms and many organics, the spin orbit coupling, sorry, my spelling is off, tends to be on the order of like tens of wave numbers. That is small, small, small. That doesn't do much. However, guess what? It turns out because of that change in potential with respect to R, for heavy elements, the spin orbit can be on the order of 10,000 wave numbers. So what's happening is here, for light elements, this guy is tiny. For heavy elements, it's big. And it has to do with the fact that heavy elements have really positive nuclei, extremely positive. So if an electron gets closer to it, it drops in energy by a tremendous amount. So because this is so big, for heavy elements, the spin orbit coupling can get, thousands, tens of thousands times bigger. Now again, for the next component of this class spectroscopy, this is about, that's around 800 nanometers. It's approaching, it's technically infrared, but it's approaching visible light. That's a fancy way of saying that's a fairly large amount of energy, and it's very significant. Now, why does that matter? Now, remember that a wave function is going to have a space part, let's say a 2s, because I'm talking about spin orbit coupling. I'm going to have to put this in like an S state. It has an alpha. It's spin up. Okay, great. Now recall that. Here, let me make it multi-electron. Let's say it's a 1s, 2s, H minus atom, something like that. So it's an alpha. Let's make it a sigma. And I'm just kind of making that up. One of the problems about this is that this is wrong. No. And that's because of the this term. I wrote it screwed up. Sorry. I got to get it right or the world will blow up. Okay. Because of the coupling in the Hamiltonian that's non-separable, this is a mistake. It's a big mistake. I can't separate these things, but I just do it anyway. You know what? Let me change. Let me do this slightly differently. Sorry. I hate it when I do that. Sorry. R, radial. Then you've got yourselves. Then you've got yourself. You know what? I have to. Yeah, if I'm going to do spin over coupling, I'm sorry. I need to make one of these a p state, right? I have to make the second electron. I have to make it a p state. I'll make the first one an S state, and I'll make one of them alpha and the other one beta. Sorry about that. Okay. Now again, I can't emphasize enough, you can't do this because you have a non-separable Hamiltonian. But notice what I've done here. I've split off my angular and my spin parts as well. Yet I've got a Hamiltonian with L and S in it. So guess what? And it's non-separable. So what does that make this?
Not separate.
Wrong. It makes it wrong. You cannot cleanly separate the angular and spin parts of a wave function because of spin orbit coupling. Now normally in organics and hydrogen, it's so small you can just erase it and not worry about it. That's why I didn't show it to you before. But when it comes to heavy elements, that's no longer true. Now the consequence is, let me show you real quick, the wave function for a singlet is no longer truly singlet. What happens is there's bleed through. There's bleed through in spin for heavy elements. It turns out that singlet states start to mix in a little triplet. That's the way you want to think about this. And here's a little diagram I wanted to show you. Let's think of singlet and triplet as being orthogonal vectors. Remember how a word for a wave function is an eigenvector? Right? This is where this is useful. A singlet wave function is thought to be orthogonal to a triplet wave function. And that means that they have nothing to do with each other. But spin-orbit coupling is like something that introduces an angle to the wave function, such that it is mostly singlet, but picks up a little triplet character, right? And the more that you have spin-orbit coupling, the more spin-orbit coupling you have, the more you bend the wave function into the triplet space. And so anyway, the point of this is that singlet states start to become slightly triplet, which is a function of how heavy the element is, where it's at the periodic table. All right, anyway, so that's that. I'll talk a little bit more about that on Monday in order to review, but regardless,